Modern Computer Vision Fundamentals. We will turn the article into one complete visual lesson. Pixels, color, locality, features, segmentation, camera geometry, reconstruction, motion, latent prediction, and collapse control. Think of the lesson as a climb from apprentice to master. At the bottom, you only see colored tiles. At the top, you can reason about objects, motion, cameras, hidden features, and the failure modes of the features themselves. Every equation is a tool picked up for one reason. It solves a specific obstacle on that climb. Real-world analogy. The whole course is a field notebook where each page adds one practical instrument for reading a scene. Computer vision is the organization of visual evidence. Pixels are sampled numbers. Local patterns become object evidence. Objects become scenes. Camera geometry turns scenes into measurable three-dimensional worlds. Modern models often reason over latents, but these fundamentals still define the problem. The real-world analogy is evidence organization. A detective does not solve a case by staring at dust. They sort traces into clues, clues into suspects, suspects into a scene, and the scene into a story. Computer vision follows the same ladder. Remember this because every later model, even a giant foundation model, is still trying to preserve the evidence needed for that ladder. Real-world analogy. Computer vision works like a detective board, turning loose clues into suspects, timelines, locations, and a coherent case.
First we turn light into evidence.
We start with image representation. A grayscale image is a two-dimensional array. Each entry is a pixel intensity. 0 means black, 255 means white, and values between them are shades of gray. The highlighted row forms the center of a white cross. The 2D array is the first spell because cameras had to become machines before they could become intelligence. Film stored chemistry. Digital sensors store sampled light. The grid shape is not arbitrary. Rows and columns mirror the sensor layout. That is why every later convolution, patch token, mask, and depth map still inherits the image grid. Real-world analogy. A grayscale image is a tiled floor where each tile has one brightness label, from black stone to white stone.
A picture can start as a table of numbers.
A color image adds a channel dimension. Height by width by 3 means every pixel stores red, green, and blue values. A pure red pixel is maximum red and 0 green and blue. White is maximum on all channels. Black is 0 on all channels. RGB came from display hardware and human color perception. 3 cone responses are enough to reproduce many colors for human eyes. The 3 numbers are not 3 objects. They are 3 measurements of the same tile of light. This matters in real systems because bad channel handling breaks medical images, satellite data, color segmentation, and generative models before learning even begins. Real-world analogy. An RGB pixel is like 3 dimmer switches on one stage lamp, mixing red, green, and blue light into one color.
3 channels, 1 color tile.
To convert RGB into grayscale. Computer weighted average. R is the red channel. G is green and receives the largest weight, 0.587, because human vision is most sensitive to green. B is blue and receives the smallest weight. The result is stored as an unsigned 8-bit intensity. The grayscale equation came from psychophysics and television standards. Engineers needed one brightness channel that looked right to humans. It is not an equal average because equal weights would overvalue blue and undervalue green. The equation is a treaty between physics and biology. Keep the brightness people actually perceive, then throw away color when the task only needs shape or texture. Real-world analogy. Grayscale conversion is like a sound mixer giving the green channel the loudest fader because human eyes hear that channel most.
Green gets the loudest vote.
HSV separates color into hue, saturation, and value. First normalize red, green, and blue into 0 to 1. The maximum channel gives value, or brightness. The difference between maximum and minimum drives saturation. Hue is the color angle determined by which channel is largest. HSV exists because RGB is awkward for many real decisions. If a robot searches for a red emergency button, it wants color identity separated from shadow and glare. Maximum and minimum channels reveal how bright and how pure the color is. The hue branch turns channel dominance into an angle. The shape looks piecewise because color space is a cube being unfolded into a wheel. Real-world analogy. HSV is like a paint shop label. Hue names the color, saturation says how pure it is, and value says how much light is in it.
Hue is the color direction, value is the light.
Next comes locality. Convolution slides a small kernel across an image. At output location XY, F supplies local image values, G supplies kernel weights, and the double sum multiplies matching entries and adds them. This is the clearest example of a local visual operation. Convolution is old signal processing armor. It came before deep learning because engineers needed one rule that could detect the same pattern anywhere in a signal. The shifted G term is there so the same stencil can be reused at every location. This is why convolution became the backbone of early neural vision. Shared local evidence gives translation tolerance without learning a separate detector for every pixel. Real-world analogy. Convolution is like sliding a small stencil over a map and scoring how strongly each neighborhood matches the stencil.
A tiny stencil scans the scene.
The code version extracts a local region from the image, multiplies that region by the kernel, and writes the sum into the output. The kernel size controls how large the neighborhood is. Valid convolution uses only positions where the full kernel fits. The code reveals the equation's machinery. A region is the local evidence under the stencil. The kernel is the question being asked. Is there an edge, blur, corner, or texture here? The sum compresses the local answer into one number. This is best when the clue is local, which is why it is still excellent for texture, edges, and early feature extraction. Real-world analogy. Valid convolution is like stamping only where the full stamp fits on the paper, then recording one score at the stamp center.
Region times stencil equals one response.
Sobel X compares left and right sides of a neighborhood, so it responds to vertical edges. Sobel Y compares top and bottom, so it responds to horizontal edges. A Laplacian looks for rapid second derivative changes. A box blur averages a local patch. Sobel filters became classics because raw differences are too fragile, while Sobel quietly smooths in the perpendicular direction as it measures change. The larger middle weights say the center row or column matters more. Laplacian asks a harsher question. Did the intensity change and then change back? These kernels are not the final hero now, but they teach gradient thinking, and gradient thinking never left vision. Real-world analogy. Sobel and Laplacian kernels are like running fingertips over a surface to feel ridges, grooves, and sudden bumps.
Edges are sudden local changes.
A Laplacian of Gaussian combines smoothing and edge detection. R squared is distance from the kernel center. Sigma squared controls scale. The exponential gives the Gaussian falloff. Multiplying the response by sigma squared normalizes across scales, which helps blob detection. The Laplacian of Gaussian is the Mahr-Hildreth idea. First calm the noisy mosaic, then look for meaningful change. Sigma is the lens size. Small sigma catches fine scratches. Large sigma catches broad blobs. The sigma squared normalization is there because bigger lenses naturally dilute the response. Without it, scale would win by accident instead of evidence. Real-world analogy. Laplacian of Gaussian is like wiping dust from a lens before judging which marks are real scratches.
Blur before measuring the sharp stuff.
Now we move from hand-designed filters to learned features. Boundary evidence can be written as differences between nearby feature vectors. dx compares neighboring columns. dy compares neighboring rows. Large changes mark likely object edges, depth discontinuities, or occlusion boundaries. Boundaries are where one explanation of the image stops and another begins. Old edge detectors used intensity. Modern networks use learned features, but the logic is the same. dx and dy are tiny arguments between neighbors. When the disagreement is large, the scene may contain an object edge, a depth cliff, a shadow boundary, or an occlusion. Real-world analogy. Boundary evidence is like listening for where two neighboring witnesses disagree sharply about what they saw.
Object edges are feature disagreements.
A vision transformer turns an image into patch tokens. The code reads height, width, and channels, slices a 16 by 16 patch, flattens it into a vector, projects that vector into an embedding, and stacks all tokens into a sequence. Patch tokens are the moment the story enters the transformer era. The image is chopped into visual words because attention expects a sequence. The projection is a learned dictionary. It turns raw patch pixels into a vector the model can compare, mix, and route. This matters because VIT, diffusion transformers, and many video models all start by making this translation from grid to language-like sequence. Real-world analogy. Patch tokens are like cutting a photo into labeled trading cards so attention can compare and route the cards.
Patches become visual words.
Promptable segmentation encodes the image once into dense features. A prompt embedding, such as a point, box, click, mask, or text instruction, conditions those features. The mask decoder returns candidate masks and quality scores. Segmentation is the mask maker's contract with the world. A class label says there is a car. A mask says exactly which pixels belong to it. The prompt embedding exists because modern interfaces are interactive. A click, box, text phrase, or previous mask can steer the same encoded image toward a new object. This is why segmentation connects editing, robotics, tracking, and medical imaging. Real-world analogy. Promptable segmentation is like asking a careful tailor to cut cloth around exactly the object you point to.
A point, box, click, or text prompt can shape the mask.
Modern image and video generation still follows the same visual principles. An encoder compresses video into latents. A tokenizer turns latents into space-time tokens. A transformer predicts new tokens. The inverse tokenizer and decoder turn them back into visual data. Latent generation looks magical, but it is a disciplined compression story. Pixel space is huge and expensive, so the encoder keeps the visual information that matters. Tokens let the transformer plan relationships across space and time. The decoder pays the debt by returning to pixels. Care about this because generation fails exactly where latents forget small objects, geometry, occlusion, or temporal consistency. Real-world analogy. A latent video pipeline is like packing a film into a travel case, planning with the compact contents, then unpacking it again.
Generation still depends on locality, attention, and geometry.
Camera geometry explains projection. A world point X is rotated and translated into camera coordinates by R&T. The intrinsic matrix K maps camera coordinates into homogeneous image coordinates. Finally, divide X and Y by depth Z to get pixel coordinates U and V. The pinhole camera model is ancient in spirit. Camera obscura, Renaissance perspective, and projective geometry all discovered that straight rays explain images. R&T move the world into the camera's viewpoint. K represents the camera's internal ruler. Dividing by Z is perspective itself. Far things shrink because the same size subtends a smaller angle. Real-world analogy. Camera projection is like a pinhole shadow theater, where 3D actors cast 2D positions on the back wall.
Depth divides the image coordinates.
The projection code follows the equation exactly. R times the three-dimensional point plus T gives the point in camera space. K maps it into homogeneous image space. Dividing by the third coordinate converts homogeneous coordinates into pixels. The code exists because projection is the bridge between simulated worlds and real pixels. If you can project a 3D point into an image, you can score whether a reconstruction is right, render augmented reality in the correct place, or train a model with synthetic labels. The homogeneous divide is not a trick. It is the price of converting projective geometry back into pixel coordinates. Real-world analogy. Projection code is like a surveyor translating a world coordinate through the camera pose and ruler until it lands on a pixel.
3 dimensions land on 2 pixel axes.
The intrinsic matrix K stores the camera's internal pixel geometry. Fx and Fy are focal lengths in pixels. Cx and Cy are the principal point, usually near the image center. K is the ruler that turns camera coordinates into pixel measurements. K deserves memorization because it separates camera hardware from world geometry. Focal length controls zoom. The principal point tells where the optical axis hits the sensor. Once K is known, 2 cameras can discuss the same 3D world in a shared mathematical language. Without K, depth and pose estimates drift because pixels have no calibrated scale. Real-world analogy. The intrinsic matrix K is the camera's measuring tape, marking zoom and the center of the image sensor.
Calibration learns the camera's ruler.
Checkerboard calibration works because the three-dimensional grid points are known. The algorithm detects their two-dimensional image corners, appends object points and image points across many views, and solves for intrinsic K plus lens distortion coefficients. Checkerboard calibration became popular because it is practical genius. The board gives many known 3D points on a flat pattern that is easy to print and detect. Zhang's method made calibration accessible by using multiple flat views instead of expensive 3D rigs. It is best when you need real cameras to measure, not merely take pretty pictures. Real-world analogy. Checkerboard calibration is like teaching a ruler its own bends by showing it a grid whose square sizes are already known.
Known squares reveal lens distortion.
Reconstruction builds three dimensions from multiple views. Structure from motion extracts repeatable features, matches corresponding points between images, recovers camera motion, and triangulates rays to estimate three-dimensional points. Structure from motion is archaeology with photographs. Every image is a fragment, and repeatable features are the shard edges. Extract, match, pose, triangulate is the reconstruction ritual. It fits the story because local features and camera projection finally work together. Visual evidence becomes geometry. Real-world analogy. Structure from motion is like reconstructing a statue from postcards taken around it.
Multiple views turn flat photos into structure.
Feature matching uses descriptors from two images. K nearest neighbor matching returns the best and second best match. Lowe's ratio test keeps a match only if the best distance is clearly smaller than the alternative, rejecting ambiguous correspondences. Lowe's ratio test survived because matching is full of imposters. The best match alone is not enough. A bland corner may match many places. Comparing best to second best asks whether the winner is distinctive. That is why the threshold is a gatekeeper for 3D. One bad correspondence can bend an entire reconstruction. Real-world analogy. Lowe's ratio test is like accepting a fingerprint only when the best suspect is much better than the runner-up.
Ambiguous matches are rejected.
Two-view geometry starts with the essential matrix E, which links matched points between calibrated views. Recover pose extracts relative rotation and translation. Projection matrices P1 and P2 define the two cameras, and triangulation estimates the three-dimensional point X. The essential matrix comes from epipolar geometry, the constraint that a point in one camera must lie along a line in the other. It exists because two perspective views are not independent. Recovering R&T turns that constraint into camera motion. Triangulation then intersects the two rays. This is the moment flat evidence earns depth. Real-world analogy. Two-view geometry is like crossing two sight lines from different windows to locate the same object in space.
Match points, recover cameras, lift rays into 3 dimensions.
Bundle adjustment refines the whole reconstruction. Observed two-dimensional points are where features appeared in the photos. The projection is where the current camera and three-dimensional point estimate predicts them. Least squares adjusts cameras and points to minimize squared reprojection error. Bundle adjustment came from photogrammetry, long before neural networks. It is called bundle adjustment because each 3D point sends a bundle of rays into many cameras, and the algorithm adjusts all rays to agree. It is best used after an initial reconstruction, because it refines the entire scene by asking the fairest question. Do the 3D points land back on the pixels where they were observed? Real-world analogy. Bundle adjustment is like tightening all camera rays together until every photograph agrees with the same 3D model.
The best 3-dimensional model reprojects back onto the photos.
Motion begins with Lucas Kinect optical flow, which assumes brightness constancy over a small motion. Ix and Iy are spatial gradients. It is frame-to-frame change. U and V are horizontal and vertical motion. A local window supplies enough equations to solve for the motion vector. Lucas Kinect optical flow was designed for small motions and local windows. Brightness constancy says a patch keeps its appearance while it moves. The single pixel equation has two unknowns, U and V, so a window collects many pixels to form a solvable system. The equation is opaque. Motion explains change, but only if the local texture has enough gradient to reveal direction. Real-world analogy. Optical flow is like following a painted dot on a conveyor belt by asking which small motion explains the brightness change.
Motion is the shift that explains changing brightness.
The optical flow code computes Sobel gradients in x and y, then subtracts the first frame from the second to get time change. A stacks local gradient samples, b is negative time change, and the normal equation solves for the flow vector. The code shows why flow is fragile and powerful. Sobel gradients measure spatial slopes. IT measures time change. A transpose A accumulates the window's evidence. Solving the normal equation chooses the motion vector that best explains all pixels together. It is best for small, coherent motions, and it teaches the core idea behind modern video consistency. Real-world analogy. The optical flow linear system is like polling a local crowd of pixels so their combined vote estimates one arrow of motion.
Every window votes for a motion arrow.
A Kalman tracker keeps a state vector, x, y, velocity x, and velocity y. The transition matrix predicts that position advances by velocity. The measurement matrix says detections observe only x and y. Prediction and correction blend motion history with new evidence. Kalman filtering entered engineering through control, tracking, and space navigation. Its genius is humility. Predict with your motion model, then correct with noisy measurement. The state includes hidden velocity because position alone cannot explain future movement. The matrices are not decoration. They declare what the world does and what the sensor can see. Real-world analogy. A Kalman tracker is like a navigator who predicts the next position from speed, then corrects course when a new sighting arrives.
Predict first, measure second, blend both.
Multi-object tracking assigns detections to predicted tracks. The cost matrix stores distances between each detection and each prediction. Hungarian assignment chooses the low-cost pairing. Matches below the threshold update tracks. Unmatched detections start new ones. Hungarian assignment turns a crowd scene into a disciplined matching problem. Every detection wants a track. Every track wants a detection. And the cost matrix prices each possible pairing. The threshold prevents absurd matches. This is why trackers keep identity through a sports play, a warehouse robot shift, or a surveillance video. Real-world analogy. Multi-object tracking is like assigning name tags in a busy station by matching each new sighting to the most plausible path.
Keep identities stable as objects move.
Self-supervised representation learning brings us to JEPA. The context encoder embeds visible patches. The target encoder embeds hidden or future patches. The predictor maps context embeddings to target embeddings. The loss compares embeddings, not raw pixels. JEPA enters when labels are scarce but video is everywhere. The painter who must reconstruct every pixel wastes energy on leaves, noise, and sparkle. The detective predicts the meaning of the hidden region in latent space. That choice came about because representations should store what supports recognition, planning, and dynamics, not every accidental detail. Real-world analogy. Self-supervised latent prediction is like a detective describing the hidden half of a photo instead of repainting every leaf.
Be a detective, not a pixel painter.
In an IJEPA style step, the image becomes patch tokens. The mask splits visible context from hidden targets. The context encoder is trained. The target encoder is frozen for this step. The predictor uses context and target positions to predict target embeddings, and mean squared error is computed in latent space. The IJEPA step is a training story with tension. The mask creates the mystery. The context encoder sees only part of the evidence. The target encoder knows the hidden answer but does not receive gradients this step. The predictor must infer the missing embedding from context and position. Mean squared error is used because the target is a vector, not a class. Real-world analogy. An IJEPA training step is like covering pieces of a puzzle and asking the model to describe the missing pieces from context.
The loss lives in representation space.
After gradient descent updates the context encoder and predictor, the target encoder follows by exponential moving average. EMA times old target weights plus 1 minus EMA times context weights creates a slow teacher, reducing trivial matching shortcuts. The EMA target is a defense against collapse and instability. If both sides chase each other at full speed, they can agree on nonsense. A slow teacher gives the student a steadier target. This is why asymmetry shows up across modern self-supervised learning. The system needs a way to learn agreement without falling into a trivial agreement. Real-world analogy. The EMA target encoder is like a slow teacher whose answer key changes gradually while the student learns.
The slow target prevents cheap shortcuts.
A latent world model rolls forward without decoding pixels. The encoder maps the current observation to latent Z for each action. The predictor produces the next latent. The trajectory is a sequence of imagined latent states useful for planning and probing. A latent world model is the vision system learning to imagine. Instead of drawing every future pixel, it rolls forward the state that matters for action. Robotics cares because planning in pixels is expensive and error-prone. If the latent contains position, velocity, obstacles, and intent, the agent can reason several steps ahead without repainting the world. Real-world analogy. A latent world model is like planning a route on a compact map instead of redrawing the entire city at every turn.
Plan in latents, not raw frames.
Representation collapse is the failure mode to watch. Total collapse maps all examples to one point. Dimensional collapse uses only a small slice of the embedding space. Regularization forces variance and decorrelation, and monitoring checks standard deviation and effective rank. Collapse is the final boss because latent prediction has a loophole. If every input maps to the same vector, prediction becomes easy and learning dies. Total collapse is obvious. Dimensional collapse is sneakier because some variance remains while most dimensions become useless. You need to remember collapse because every self-supervised method must defeat it. Real-world analogy. Representation collapse is like every student writing the same answer for every question, making agreement meaningless.
If every answer is 42, nothing was learned.
The variance term keeps every embedding dimension alive. Standard deviation is measured across the batch. The hinge penalty activates only when a dimension falls below the variance floor. This prevents silent constant dimensions. The variance term is a life support monitor for embeddings. It measures whether each dimension changes across the batch. The hinge shape is important. It does not reward infinite variance. It only punishes falling below the floor. That makes it a guardrail rather than a demand to encode noise. Real-world analogy. The variance term is like checking that every gauge on a dashboard still moves when different examples arrive.
Dead dimensions get pushed back up.
The covariance term prevents dimensions from becoming copies. First center embeddings by subtracting the batch mean. Then compute the covariance matrix. Remove the diagonal, because self-variance is allowed. Penalize squared off diagonal entries to reduce redundant correlations. The covariance term asks a different question. Are dimensions learning different jobs? Centering removes the batch mean so covariance measures co-movement. The diagonal is removed because a dimension may vary with itself. Off-diagonal penalties push dimensions away from copying each other, preserving capacity for downstream tasks. Real-world analogy. The covariance term is like stopping a team of analysts from all doing the same job and wasting the remaining desks.
Features should spread out, not copy each other.
Effective rank catches hidden dimensional collapse. Singular values describe how strongly the embedding batch uses each direction. Normalize them into a distribution. Compute spectral entropy, and exponentiate. A higher effective rank means more dimensions are really being used. Effective rank is the spectrum's confession. A model may look healthy if you inspect one statistic, but singular values reveal whether the batch really spreads through many directions. Entropy turns that spectrum into a soft count of active dimensions. It is memorable because it catches the quiet version of failure. Real-world analogy. Effective rank is like counting how many instruments in an orchestra are truly playing rather than watching the conductor only.
A wide embedding should actually use its width.
The transformer paper matters to vision because images and latents can be tokenized into sequences. Patched tokens become embeddings. Attention models long-range relationships. Encoders produce contextual features that downstream decoders use for masks, generation, and other tasks. Transformers fit the story because attention generalizes the journey from local clue to global scene. Convolution asks strong local questions. Attention lets every token ask which other tokens matter. Modern vision needs both instincts. Respect nearby evidence, then connect distant objects, frames, and views into one explanation. Real-world analogy. Transformer attention is like a control room where every camera feed can ask which other feeds matter right now.
Local evidence and global attention now work together.
SkyJeeper is a recent example of the same fundamentals. Encoders map raw observations to latents. JIPA predicts future latent states. SIG-reg keeps representations from collapsing. Probers test whether frozen latents contain physical quantities such as velocity and attitude. SkyJIPA shows why the fundamentals are not museum pieces. A quadrata needs latents that preserve dynamics, not merely pretty reconstructions. SIG-reg fights collapse so the representation remains useful. Probers then ask whether velocity and attitude are actually encoded. The old story of evidence, motion, and geometry reappears inside a modern world model. Real-world analogy. SkyJIPA is like a pilot training in a compact flight simulator that preserves dynamics instead of painting every pixel.
Modern systems still lean on the fundamentals.
The takeaway is simple. Modern architectures change quickly, but visual evidence, geometry, masks, motion, three-dimensional consistency, latent prediction, and collapse control remain the load-bearing ideas behind computer vision systems. The final lesson to ingrain is that computer vision is not a bag of equations. It is a chain of responsibilities. Preserve evidence, respect locality, separate objects, calibrate cameras, recover structure, track motion, learn latents, prevent collapse, master that chain, and new architectures become easier to understand instead of intimidating. Real-world analogy. The final system is like an engineering checklist that keeps evidence, geometry, masks, motion, latents, and stability aligned.
That is the foundation modern vision keeps building on.
End of complete video. The climb is complete, but the tools remain in your kit. Real-world analogy. The finished video leaves you with a packed toolkit, ready for the next visual problem.